I think we can start today's webinar. First of all, a warm welcome to everyone who joined. My name is Niels, and I will take over. Unfortunately, Tasneem won't be able to host today. As I mentioned, my name is Niels, and I'm one of the customer support engineers at Diabatix. So if you have any technical questions, you will for sure get in contact with me again. For today's webinar, we'll be focused on enhancing battery cold plates, or the performance of battery cold plates, through design optimization. And more specific, we will focus on initialization. This part is this webinar, is a follow-up on a previous webinar given by Tasneem, which focused on the concept generation, so considering dimples, circular dimples, and rectangular dimples. So I will skip most of those parts. But if you are curious or you didn't watch it, you can rewatch it, of course, on our website. That's enough about the introduction. Let's move on to today's talking points, which is, of course, first to give a more in-depth introduction to Diabatix for the ones who are new, and to ColdStream. Later on, we can move on to the most interesting part, the technical discussion on what initialization is, what initialization options we have available, and what we recommend or how we recommend tackling a workflow. We'll then apply those learnings on a case study, of course, the battery cold plate, and lastly, we'll end with a Q&A session. If you have any questions throughout this webinar, feel free to put them in the chat box. Our moderators are following along, so they will already answer some of those questions. And any interesting questions or any open questions, I will answer towards the end. And let's try to keep this within the 30-minute mark. So I'll move on. First of all, for those who don't know Diabatix, we at Diabatix strongly believe that smart algorithms can boost the performance of thermal engineers, both in outputs, basically the quantity of designs per unit of time, as well as in the quality of those designs, so the performance of those designs. So that's where we focus on making those smart algorithms available. On the top right, you see two of the very big names within the CFD world. Both ANSYS and Hexagon have acknowledged the strength of our software, have reached out to us, and we made them our technology partner. Okay, on the left, we can now move on to how to design a heatsink. On the left, you see the conventional way of working, where you start from an empty shape where cooling structures can be generated. You first create a couple, either based on previous experience or based on a paper that you may have found online. You then typically run a CFD simulation or do some physical experimentation. You post-process the results, you analyze it, and you loop through this until you get a solution. As you can imagine, it's quite labor intensive, and depending on your speed, it can take a bit of time. On the right hand side is the alternative approach, where again we start from the same input, an empty geometry, where heatsinks or where cooling structures can be placed. And in the first step, you can use generative design then to generate a wide variety of different concepts to explore how a design change affects the performance. This part is tackled in Tasneem's webinar from a couple of weeks ago, so I will not go too much in depth. But let's say if none of those concepts meet the thermal requirements, you then have to move on to what we call detailed design generation, and that's where we will focus on to get the most, to basically extract the maximum out of it, to really meet, to get as close as possible to all the thermal requirements. This slide deck, perfectly summarizes how a typical workflow looks like. Early on, the hourglass is wide. Try a bunch of different options: spins, fins, gyroids, different kind of dimples. Split the design domain up in multiple parts. Try your wildest in those in the first stages, but then narrow down to a couple of variables in detailed design And lastly, when you have optimized for a given operating condition, and you want to know how that design performs for different operating conditions, you can then widen again for the sensitivity analysis in the thermal analysis phase of the design cycle. As I mentioned, this is tackled in a previous webinar, so feel free to rewatch that. And we will then move on to initialization. So the main difference between concept generation and detailed design generation is with standard design, so with the concept generation, you a priori fix design philosophy. For example, if you take pins, or if you select pins, you can change the width of the pin, the height of the pin, the number of pins, the placement. Is it structured or is it unstructured? But that's pretty much it. You will always get a pin design, which in most cases is perfectly fine. But if you want to really extract the maximum out of it, you'll have to go with a detailed design generation, where you can then leverage AI to extract the maximum out of it and to get something intricate looking, like you see here on the bottom. Okay, that's a bit of the introduction to how usual workflow looks like. We can now move on to concept generation and how it ties in then to initialization. On the screen, what you see here is on the x-axis, the design variables. So basically, you can think of it of all possible heatsinks that can be used. And on the y-axis, the performance values of those designs. It's an optimization, so do take into account the lower the value, the better. It's a bit counterintuitive, but with optimization, it's always a minimization of something. Okay. With the concept generation, what you basically attempt is sampling of the entire design space. So let's say with pins, let's call that concept 1. You try all your variations with pins, so changes in width, height, etc. And that will give you this graph. And then the lowest point is then the most optimal one of all of the pins. Try then the same with fins. Try the same with circular dimples, rectangular dimples, gyros, etc. You try all of these different things, and it might be, or in most of the cases, it is sufficient that one or a couple of them will meet your thermal requirements. So that's my first green arrow or green line here. Sorry. Both concept 1, 2, 3, and 4 have generated a design that meets my thermal requirements, and then I'm done. I can move on to prototyping, or I can move on to the next cooling requirements. However, if my thermal requirements need to meet this line, then none of them meet my requirements, and then I have to move on to the detailed design generation. But luckily, I don't have to start from scratch. I can use initialization, basically giving an initial jumping point for the optimizer to start from, to then get to a design that meets my target. If I start from concept 1, it's, as you can see, it has to overcome this hurdle to then get to the global optimum. In theory, ColdStream can do it, but as you can imagine, it will take time to overcome this hurdle, and it will take quite a few iterations, design iterations, to then move or to get to a design that's close to the global optimum. While if you start from concept 2 or concept 3, that's basically moving downhill. That's much easier, much faster to then get to the final optimal design, or to get to a design that meets your real target. And that's where the strength lies in using that initialization. ColdStream offers 3 initialization modes. A bit counterintuitive, but I will start from the right. Only add is an initialization where your initial design is untouched. For example, if you use pins, the pins will not be changed. ColdStream can only add material in between the different pins. For example, if you have 2 pins next to each other, ColdStream can add a bit of material in between to make a small fin, or you can group a couple of pins into a bigger structure. But the underlying initial design is fixed. Only remove is the complementary mode. The channels of your initial design are untouched. ColdStream can only take away material from your initial design. Let's take again our pin example. ColdStream can then decide which pins to keep and which pins to remove, which is, for example, very good in a weight minimization setting where you have a maximum performance temperature target, and a weight minimization target. In that scenario, ColdStream will then take away the pins that has the least contribution to the heat exchange. So these are very robust modes, but as you can imagine, they're a bit limited in what they can do. While the only remove, the add and remove is a combination of both. ColdStream can add material in between the channels of your initial design, or it can take away material from your initial design. So this is, of course, more powerful, and this is the mode that can get you from concept 1 to the global optimum. But in certain scenarios, and that's something that we'll cover later, one of these makes more sense. Okay, let's now apply that knowledge to a ColdStream case. This case that being ColdStream is quite easy. You upload a cut file, you set the solids and the fluids. So is it copper, aluminum, is it water that will be used, or water glycol, or regular air? Next, you set the boundary conditions. Is it forced convection, natural convection? What does the heat load look like? And then in the design domain, the volume where ColdStream is allowed to modify the geometry, you then upload your initial design. And lastly, of course, you set the targets. Maximize heat exchange efficiency is a very common one. Constraining the pressure drop is another one. We have 20+ targets that you can mix and match however you see fit. And that's basically pretty much it. Once all that information has been provided, ColdStream can then start computing, and after a short while, you will then get the final design in step file format. As a bonus feature, ColdStream will take manufacturability into account from the start. So depending on what or how your design will be manufactured, you can then fine-tune those settings to make sure that whatever ColdStream outputs will meet your manufacturing constraints. So for battery cold plates, sheet metal forming is by far the most popular option, where I can specify, for example, minimal and maximal channel width. Maximal channel width is, of course, very important to make sure that the pressure exerted by the fluid doesn't result in permanent deformation of the plate, as well as minimal and maximal structure width size. Minimal size, of course, being very important to glue or to weld the stand plate to the top plate for structural reasons. And then some additional settings like deformation angle, fillet radii, etc., where you have all full control over. Okay, that's enough of an introduction. Let's now move on to ColdStream itself. Yes. So this is ColdStream, or at least the main landing page after you log on to the software, and that is the project overview. As the name implies, the project overview gives an overview of all different projects to keep everything nice and tidy. If I then scroll down to this project, yes, we will then see all of the cases, or what we call the cases, all the engineering problems that you want to solve in ColdStream. 3 case types are available. If first of all, you start with a simulation, of course. If you have a design or just want to know the performance of the empty geometry, you can use a simulation to measure that performance. So it's a simple CFD simulation. Next, we have standard designs, so that's the concept generation, where the design philosophy is fixed, and then ColdStream will optimize the parameters that govern those conventional cooling solutions. And lastly, we have the custom design, the detailed design generation, so to get to extract the maximum out of it. And as you can see from this, we mainly focus on the constant generation. As I mentioned earlier, it's the white part of the arrow glass. Focus a lot on constant generation and those validations, and only then move on to the detailed design. Let's quickly start by going over the standard design case to highlight the constant generation cases, or the constant generation capabilities, rather. Yes, and to also explain a bit on what the case setup looks like. So it's a simple battery cold plate where we have a cover, basically the part that sits on top of the battery pack. The battery pack itself is simplified. We assume a uniform heat load over the contact area. We then have the fluid domain, so basically the dictates where the fluid can flow. And lastly, we have the stem plate, or parts of the stem plate, which remain fixed, where ColdStream cannot change the design. Once you prepare that CAD geometry, you can then click on each of the entities and fill in the information. So starting with the cover, that's of course a solid, in this case made out of aluminum, and it doesn't produce any heat. This is sufficient. We then move on to the battery pack. Here, seeing as we simplified it, we assume a binary condition. You can click on the drop down what type of binary type you want to select. Here it is a heated wall to insert a given heat flux, where in total just below 4 kilowatts of energy will enter through the domain. And we want, of course, to minimize the temperature, or equivalently maximize thermal uniformity. Maximize heat exchange efficiency. And we constrained the temperature variance. So we let ColdStream know whatever you design, the difference between maximum and minimum temperature should be at least within a given range. This is something that we repeat then for the fluid. Now, of course, it's of type fluid, where regular water will be used. We have an inlet condition here on the right, where we specify again a flow rate. If you want, you can switch it to a pressure inlet or a fan inlet or a pump inlet. And then we specify how much flow enters and at what inlet temperature. And here, of course, we don't want the pressure drop to exceed very high, so we put a pressure loss constraint to make sure that whatever ColdStream designs, the pressure between in and outlet will never exceed, in this example, 6 kilopascal. Then we have the outlet, just a regular pressure outlet condition. And finally, we have the design domain. So the design domain is the volume where ColdStream is allowed to modify the geometry. And in the constant generation phase, you see here all of the options that are available to you. So if you scroll down to sheet metal forming, you then have control whether or not you want to consider circular or rectangular dimples. Okay, that's pretty much it. So in the constant generation case, what we did here is we took one case, looked at circles, another case looked at rectangles, and then we noticed our battery pack is quite long. The incoming flow here is very cold, it hasn't heated up yet, while here towards the end, the fluid or the coolant has taken on energy, has increased in temperature. So it's very unlikely that our design, or the most optimal design, is a uniform one. So what we did in the next couple of steps was to split the design domain up in smaller parts and retry again with circular dimples and rectangular dimples as well. Yes, and that's basically what you see here. All of those standard design cases. Just try all different variations and see what works. And in our case, we noticed then that circular dimples, with of course the different design domains, works the best. But it's not exactly, or doesn't meet our thermal requirements yet. So then we have to move on to a custom design. The input for a custom design is almost identical. So you can specify a cover with a solid aluminum, a battery pack, which is the heated wall, our targets, our thermal targets here, our fluid domain. So all of that remains the same. The only change is in the design domain. So here we can then upload an initial design. Let me quickly show it here. Hide others. Yes. So this is our initial design. You can clearly see where it originates from. We have the design domain here, a design domain here, a big design domain in the middle, and then again mirrored a smaller design domain on the top left, sorry, and another smaller design domain in the bottom left corner. And then we have our three options. Our initial design was well below the pressure drop constraints. I think it was about not even 50% of the pressure drop constraint. So in that scenario, it makes most sense to use only add. Why do you ask? We know, that's not what I want to do. We know, of course, that circular dimples, same with pins, they break up the thermal boundary layer. So the boundary layer builds up, but then because the circle ends, there is separation, causing for mixing of the fluid, which is not as good pressure drop wise, but it's very good temperature wise, because you induce mixing. All of the heat that's built up in the thermal boundary layer is mixed with the surrounding fluid, which is then beneficial later downstream. So that's a feature in this case that we want to keep. You have the margin with respect to pressure drop. So the only thing that makes sense is to only add material, increase the contact area between the sheet metal form structures and the coolant. So I hope this explains why only add is the most suitable one. Let's say if our initial design was more or less on our pressure drop constraint, then I would have chosen the add and remove to allow ColdStream to see what modifications makes most sense. And if our pressure drop in the initial design of the pressure drop of our initial design was way too high, then of course I would select only remove to take away the pins that have the least contribution to the heat transfer. And that's pretty much the only difference. So here again you specify then your manufacturing settings to let ColdStream know how or what those structures can look like. Okay, I will switch back to my slide deck. Yes. So here, a quick summary again from Diabatix webinar. So by using constant generation, we can easily, in a matter of minutes to a matter of hours, you can get hundreds of different designs. They finish very, very quickly, and they don't take a lot of resources. So giving you instant feedback on what design change works. So basically, giving you insight in splitting that design domain, does that make sense or not? And it also showcases what works and what not. We immediately noticed that the circular dimples outperform the rectangular dimples by basically outperform them. So we knew to continue with those. And then we can move on to, of course, the detailed design evolution, where when the case is running, ColdStream will output intermediate data points. The first iteration is, of course, our initial design. ColdStream needs to start from something. And then throughout the design phase, you can see that ColdStream added additional structures to increase the flow path length. So in iteration 2, it created here some structures to make or to force the flow, to snake around it. Iteration 3, there are still pressure drop available, so ColdStream again added more structures, and so on and so on. And if we look at the individual performance values, our initial design, as I mentioned, was way below the pressure drop constraint, nearly two-thirds still to play with. And iteration 2 and 3 every time increase on it, iteration 4 as well. Iteration 5 exceeded it. But if you look at the temperature variance, then we see that it's decreased compared to the initial design, as well as the temperature minimization objective, that again decreased. So this, of course, gives you as a user much more control over what ColdStream does in the background. And basically, let's say if iteration 3 already met your requirements, you can stop it prematurely and finish the case like so, to free up those resources and to move on to the next project. Are there any questions? Let me have a look in the chat box here. Someone asked a question here. So the question that was asked is, I mentioned it that if you start from concept 1, it is possible to go to the global optima and to overcome this hurdle. And the question basically is, how is that done? I have to disappoint you here. This is a company secret, and yeah, I'm pretty sure I can't disclose it. But it is, yeah, ColdStream can do it. Yeah, ColdStream can do it. But of course, it can only do that with the add and remove, where ColdStream has complete flexibility to change everything about it. While if, let's say, you start with concept 1, but you only select, for example, only add or only remove, it won't be able to do that. It will just then move to a local optimum. While for concept 2 and concept 3, that would have been possible. Let's say if he, most likely would have been possible if he click on concept 2 or use concept 2 as initialization using, for example, only add to move then to a global optimum, given of course that there is sufficient amount of pressure drop to play with. That the thing is best with those concept generations, especially to move as close as possible to the constraint, and then of course further optimize from there. Quickly looking at the time here. I don't think I'll have time for another question. So let me move on to my final slide here. If you want to try ColdStream for yourself, we do make a viewer access, or we do have viewer access enabled. If you move to this link, you can get credentials to log on to that viewer account to see what the interface looks like, etc., and to download those results. Or if you want to know more, you can contact the team by emailing to info@diabatix.com or to simply calling this number. Okay, that's it from my side. I hope you learned something, and I hope to see you in the next webinar. Have a nice day. Bye-bye.